Hey everyone, welcome back. This is lesson 11-2, Theoretical and Experimental Probability. The objectives for today: by the end of this lesson, you'll be able to find the theoretical probability of an event. You'll also be able to find the experimental probability of an event. There's a lot of vocabulary words for today, and I'm not going to read them all out, but you can turn the video off and write them down if you'd like to. All right, so probability is the measure of how likely an event is to occur. Each possible result of a probability experiment or situation is an outcome. The sample space is the set of all possible outcomes. An event is an outcome or set of outcomes. Again, if you'd like to turn your video off and write this down so you'll have it for your information, that would be great. Also, you can look at your Know It notebooks, and they have these definitions already written out for you, and you'll find the Know It notebooks in your RenWeb account. All right, so let's take a look at some examples. So the experiment or situation is rolling a number cube, or in this case, spinning a spinner. So the sample spaces, that's just how many choices or how many options there's going to be, that it could, how many outcomes there could be. So it could be 1, 2, 3, 4, 5, or 6 for the number cube, or your outcome could be red, blue, green, or yellow. Probabilities are written as fractions or decimals from 0 to 1, or as percents from 0% to 100%. So what that means is if you are at 0%, it's impossible for the event to happen. All right, if it's 50% or half or 0.5, any one of those, it's just equally as likely to happen as not happen. And if it's 100%, then it's a certain. All right, so I think you're probably pretty okay with that. All right, so equally likely outcomes have the same chance of occurring. When you toss a fair coin, heads and tails are equally likely outcomes. Favorable outcomes are outcomes in a specified event. For equally likely outcomes, the theoretical probability of an event is the ratio of the number of favorable outcomes to the total number of outcomes. And so here it is written out as an equation for you. So for equally likely outcomes, the probability of an event is the number of favorable outcomes divided by the number of outcomes in this sample space. Okay, so this is another page that you might seriously go ahead and write this chart down so you can keep that in your memory. All right, so let's try an example. The first question says, each letter of the word probable is written on a separate card. The cards are placed face down and mixed up. What is the probability that a randomly selected card has a consonant? All right, so what's the first thing we should do? Well, the first thing we need to understand is that there are 8 possible outcomes. So PR, this is, and how did I find that? I know that this is 1, 2, 3, 4, 5, 6, 7, 8 letters in all, and 5 of them are consonants. 1, 2, 3, 4, 5. All right, and the question says, what is the probability that a randomly selected card has a consonant? So that's our favorable outcome. So we have 5 favorable outcomes and 8 possibilities. So the probability of drawing a consonant is 5 over 8, or you can put that in your calculator and you get 62.5%. And actually, if you put in your calculator 5 divided by 8, remember that you're going to get 0.625, but we want to change it to a percentage, so we just need to move our decimal point 2 places over to get 62.5%. Okay, here's another example. 2 number cubes are rolled. What is the probability that the difference between the 2 numbers is 4? All right, so notice if I have 2 die being rolled, or 2 number cube, here's all the different possibilities that it could happen. I could roll a 1, 1. I could roll a 1, 2, 1, 3, 1, 4, or a 2, 1, 2, 2, 2, 3, so on. All right, so that's all of the possible outcomes. There's 36 of them in all, so 6 across and 6 down. Now, what I want to know is the ones that have a difference of 4. All right, so that's the number of outcomes with a difference of 4, and all of that is going to be divided by our total outcomes. So what we need to do is take a look at which ones are the difference of 4. Well, I know that 1 and 5, that's going to have a difference of 4. All right, I know 2 and 6, that would have a difference of 4. How about 5 and 1? Difference of 4, and 6 and 2, again, difference of 4. So there's actually only 4 of them could be the favorable outcomes. So it's 4 over 36, which is the same as 1 over 9. And you could also put it in your calculator to get the percentage too. All right, so try this one on your own. Turn your video off and give it a try. All right, again, a red number cube and a blue number cube are rolled. If all the numbers are equally likely, what is the probability of the event? And the event, the favorable outcome, is going to be the sum is 6. So there are 36 possible outcomes. We saw that in the last slide. And so now we have to figure out which ones have a sum of 6. All right, so just taking a look at it, we see again, 1, 5 has a sum of 6, 2, 4, 3, 3, 4, 2, and 5, 1. So there are all the ones that add up to 6. So I have 1, 2, 3, 4, 5 of the favorable outcomes. So 5 out of 36. I think you should probably be pretty comfortable with this. One more for you to try. This one, again, the favorable outcome is going to be the difference of 6. So turn your video off and try it real quick and see if you get the right answer. All right, so again, there are 36 possible outcomes. We have the number of outcomes with a difference of 6. That's going to be my favorable. So take a look at it. A difference of 6. There's none of them that will give me a difference of 6, okay? 6 minus 6 is 0, so that's not going to be it. 5 minus 6, that would be, or 6 minus 5. 1 minus 1, there's no way. So I have 0 outcomes that would be the difference of 6. So that tells me that the probability of that happening is 0. All right, one more for you to try on your own. This time it says the favorable outcome that we want is for the red cube to be greater. All right, so again, go ahead and turn your video off and find that. All right, so on this one, again, there are 36 possible outcomes. And we are looking for the number of outcomes with the red cube greater. And so those are, there's quite a few of them, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. And then 3, 2, 4, 2, 5, 2, and 6, 2. And then 4, 3, 5, 3, 6, 3. And then down to 5, 4, and 6, 4. And then 6, 5 finally. So we count all those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's see if I counted that correctly. Yep. So 15 out of 36 reduced to 5 out of 12. And again, you could put that in your calculator and get the percentage also. All right, so the sum of all probabilities in the sample space is 1. The complement of an event E is the set of all outcomes in the sample space that are not in E. Okay, so let's see what that really means. The complement, first of all, the probability of the complement of event E is the probability of not E equals 1 minus the probability of E. So let's see what this means. Here's an example. There are 25 students in study hall. The table shows the number of students who are studying a foreign language. What is the probability that a randomly selected student is not studying a foreign language? All right. So if we know that there are 25 students in all, but the number of students that are studying a foreign language are 12 plus 6 is 18, 21. So that tells us something. So we're going to use the complement in this case. And so here's our formula. The probability of not foreign has got to equal to 1 minus the probability of foreign. So there are 21 students studying a foreign language. So the probability of not foreign is going to be 1 minus the probability of foreign. And the probability of foreign is 21 over 25. So we're going to say 1 minus 21 over 25. And that is the same as reduced down to 4 over 25, and you could just put that in your calculator. You'd get 0.16, and we know that that's the same. Move the decimal point over to 16%. So the probability of not foreign is a 16% chance that the selected student is not studying a foreign language at all. So this is pretty important, so you might want to write this rule down. The probability of not foreign is equal to 1 minus the probability of foreign, or not necessarily not foreign, but in the event. All right, so here's one for you to try on your own. Turn your video off and give it a try. All right, so this problem says 2 integers from 1 to 10 are randomly selected. The same number may be chosen twice. What is the probability that both numbers are less than 9? So the first thing we want to do is use the complement. So the complement is going to say the probability of the number less than 9 is equal to 1 minus the probability of number greater than or equal to 9. Okay, so what numbers are greater than or equal to 9? It would be a 9 or a 10, okay? 9 or a 10. So there's actually 2 of them. So that's going to be 1 minus 2 tenths, and we could think of that 1 as 10 over 10, minus 2 is equal to 8 over 10. Now, the same number may be chosen twice, but it says 2 integers. So the probability of getting it one time is 8 over 10, but we're going to pick 2. So the second time, what I'm going to have to do is multiply that 8 over 10 times 8 over 10. All right, and that's going to give me my final answer here. Okay, I got to multiply it twice because I'm going to pick 2 integers between there. All right, so that is going to be 64 over 100, which is 16 over 25, or 64%. Okay, so example 3 says each student receives a 5-digit locker combination. What is the probability of receiving a combination with all odd digits? All right, so first we have to determine whether the code is a permutation or a combination. So hopefully by now that's an easy answer because we talked about that in class, but we know that that is going to be permutation because a digital locker combination is a permutation. It's not a combination lock, it's a permutation. All right, so order is important, so we're going to use the permutation. So step 2, we're going to find the number of outcomes in the sample space. So let's talk about that. So now we're putting everything that we've learned together. Okay, we know that we're going to have 5 numbers, and each of them we have a choice of 10 digits. So we actually have 100,000 choices. So now there are 100,000 outcomes. So now that we know the number of outcomes, now we can figure out our answer to the question about it all being odd numbers. Okay, so now we need to find the favorable outcomes. And we have 5 numbers and we want odd, and there are actually 5 odd numbers that it could be on each one. So we have 3,125 favorable outcomes. So now that we know both information, we know the favorable outcomes and how many possible outcomes, now we can find the probability. So the probability of odd numbers is 3,125 out of 100,000, and we can reduce that to 1 over 32. Therefore, the probability that a combination would have only odd digits is 1 in 32. Okay, so try this one on your own. Turn your video off and give it a try. All right, this one's a little tricky, but I think you can get it. It says a DJ randomly selects 2 of 8 ads. So there, that word randomly is helpful to us. Selects 2 of 8 ads to play before her show. 2 of the ads are by a local retailer. What is the probability that she will play both of the retailer's ads before her show? So the first thing we need to do is determine whether the code is a permutation or a combination. And order is not important here, so it's a combination. All right, so step 2, we're going to find the total number of outcomes in the sample space. So we're going to use our information on how to find a combination, and we can just fill that into our equation that we learned. And when we do, we just have to divide out the common factors, and we're left with 8 times 7 over 2 times 1. And I always like to reduce as much as possible, so I see that 4 goes into both 8 and 2, 4 and 1. So now I can see that it's equal to 28. And so now that I know that, I can find the number of favorable outcomes. So once again, the favorable outcome is playing both local ads before the show. So there is only one favorable outcome. All right, so step 4, we're going to find the probability now. There's only one way that could happen out of 28 possible outcomes, only one favorable, so we have 1 over 28. So that tells us that the probability that she will play both of the retail ads before her show is 1 over 28, or 1 out of 28. All right, let's talk about geometric probability. Geometric probability is a form of theoretical probability determined by a ratio of lengths, areas, or volumes. All right, so let's take a look at example 4. It says a figure is created placing a rectangle inside a triangle inside a square as shown. If a point inside the figure is chosen at random, what is the probability that the point is inside the shaded region? All right, so take a look at that and think about it for just a minute, what you would do. All right, so the first thing we want to do is find the ratio of the area of the shaded region to the area of the entire square. The area of the square is side square, and the area of the triangle is 1/2 base times height, and the area of the rectangle is length times width. So let's see what to do now. So first of all, we're going to find the area of the entire square. So that's pretty easy. The area of the entire square is going to be, the total area is going to equal 9 times 9, which is 81. So that's the area, length times width of the entire square. All right. So the next thing we want to do, okay, so now that we have the total area of the square, we're going to find the area of the triangle, which is shaded. So area equals 1/2 base times height. So the area of our triangle is 40.5, but the whole triangle is not shaded. All right, we have to subtract that for this rectangle. So let's find the area of that rectangle, which is base times height. So that's going to be 3 times 4 equals 12. So now we have to take our triangle and subtract that rectangular piece out because it's not shaded. All right, so 40.5 minus 12 gives me 28.5. So now I just have to find the ratio between the shaded area and the non-shaded area. So my total area of the square is going to be 81, and the portion that was not shaded, or that is shaded, is 28.5. So when you divide that through, we get about 0.352. All right, so try this one on your own. Turn your video off and give it a try. All right, so this one says, find the probability that a point chosen at random inside the large triangle is in the small triangle. So I hope that you realize that the probability that a point is inside the small triangle is the ratio of the area of the small triangle to the large triangle. So that's the key thing here. It's the ratio that we're going to be doing. All right, so we're talking about area. Now, normally we say area equals base times height, but in this problem, we're not given the height. We are given the slant height, though, and there's actually a formula for that. And so it is s squared times the cube root, or the square root of 3, all divided by 4. Okay, and so, and s is the side, so we're going to be putting 4 in here. So now that I know that, I'm going to go ahead and put my numbers in place there. So I'm going to find the area of the small triangle using that formula, and it ends up to be 4 square root of 3. So that's the area of my small triangle. Now the area of my larger triangle is going to be, again, we're going to use that same formula, and this time it is 225 square root of 3 over 4. So now I have to set this up as a ratio. All right, so it looks kind of nasty here. So the area of the small triangle in relationship or as a ratio to the area of the large triangle. And once you put those two pieces in, then we just simplify and we end up with 6 over 225. You can estimate the probability of an event by using data or by experiment. For example, if a doctor states that an operation has an 80% probability of success, 80% is an estimate of probability based on similar case histories. Each repetition of an experiment is a trial. The same sample space of an experiment is the set of all possible outcomes. The experimental probability of an event is the ratio of the number of times that the event occurs, the frequency to the number of trials. So here it is written a little bit easier to see. The experimental probability is equal to the number of times the event occurs in ratio to the number of trials. So experimental probability is often used to estimate theoretical probability and to make predictions. Example 5 says the table shows the result of a spinner experiment. Find the experimental probability. So here we see that we had some spinning here, and 19 plus 11 is 30, 40, 50. So we tried 50 times. Okay, you can look at your occurrences and you can see that we had 50 tries. All right, of those 50 tries, 1 was rolled 6 times, a 2 was rolled 11 times, 3 was rolled 19, and 4 was rolled 14 times. So we can see that the outcome of 4, because that's what our original question said, occurred 14 times out of the 50 trials. So we can just write that as a ratio, 14 out of 50, and then reduce it to 0.28. Okay, so in example 5b, we are to find the number times the spinner hits a number greater than 2. So that's going to be 3 plus 4. So that's the numbers 3 and 4 are greater than 2. And so at 3, it happened 19 times, and the 4 happened 14 times. So our probability is going to be 19 plus 14 divided by 50. And when you work that out, you end up with 0.66. Okay, try this one on your own. Turn your video off and give it a try. The problem says the table shows the result of choosing one card from a deck of cards, recording the suit, and then replacing the card. And we want to find the experimental probability of choosing a diamond. So first of all, I can look and see how many times did they do this. Well, 5 plus 5 is 10, plus 6, 9, and 7 is 16. So 26 times they tried it, and only 9 times did they get a diamond. So we can take a look at it. The outcome of diamonds occurred 9 out of 26 times. So the probability is going to be 9 out of 26. That's the experimental probability. Okay. Now realize that hearts, diamonds, clubs, and spades could all equally be chosen. But in this case, it's 9 times diamonds were chosen or picked more than the other. Okay, one last problem for you to do on your own. Turn the video off and give it a try. All right, so we're doing the same experiment. We're trying to find the experimental probability this time, and we're going to choose a card that is not a club. So I want you to remember when we're doing something that's not, we're going to use the complement. So the probability of getting a club is 7 out of 26. So 1 minus 7 out of 26 is 19 out of 26. So that's our probability of not getting a card that's a club. Pretty high. Okay, so that's the end of that. If you'd like to put your video on pause and try these 2 lesson questions and make sure you're understanding it, that would be great. Turn your video off and give it a try. Okay, so if you did those problems, you should have found that the probability for number 1 is 88%, and the probability for number 2 is 3 over 23,765. And that is the end of your lesson for today. So I hope you have a great day, and I'll see you in class. Bye.